In this video, I'll be demonstrating a TransAT simulation stratification of mixed gases. We will see the algebraic slip model and how it is computationally efficient, and additionally, how it treats each phase as a dispersed phase in the calculations. I will also show how to make your own advanced initial condition file. If you watched the oil separation tutorial, you will know how to load and compile such a file, but now I will give details how to write an advanced condition file. Our problem consists of 4 phases that are equally mixed in our domain. We have a 1D problem in the x direction of 0.02 meters. Due to gravity, the denser phases of 1,800 kilograms per meter cubed will sink to the bottom of the domain. The lighter phases will stratify on top. Let's set up our problem. In this tutorial, I will assume you are familiar with TransAT, that I can go more quickly through the setup and focus on the important points of the tutorial. First, we'll be setting the domain. And the cells. And dividing by 3 blocks in the x direction. For boundary conditions, we'll have symmetry boundary conditions on each surface. Under inputs, we need to solve for pressure and u velocity. And define gravity. Under advanced models, we'll be using the multiphase flow method with the phase average model, using 4 phases. The phase average model is what allows us to use the algebraic slip model more computationally efficient. Let us activate the drift velocity now. Under phase properties, we'll define each of our phases. Under simulation parameters, we will have an unsteady simulation for 120 seconds and a maximum of 3,500 time steps. Under equations, we'll increase the convergence tolerance slightly. And we'll also change the relative solver tolerance. We could set our initial conditions here, defining a volume fraction of 0.25 for each phase. I will refrain from doing this so that I can show you advanced initial conditions from a file. Under output management, we'll select the output variables, and we'll also output density and phase volume fractions. As well, let's select maximum values of variables. I will now briefly go over the initial conditions file. At the beginning, there are some include statements to use the header files required. And next, an extern C function is used so that TransAT can access the C++ files. Then we begin our initial conditions function. First, defining the variables that will be used. N blocks is for the total number of blocks that are in the simulation. NB is an index for the blocks. II is an index for cells. Nijk is the total number of cells. And rank is the processor index. We then have pointers for variables used in TransAT. We have u velocity, pressure, density, and alpha rho for each phase. Alpha rho is the product of volume fraction by phase density. Using a TransAT function, getInteger, we get the rank. Then the same function is used to get n blocks. we print a statement to show that the initial conditions are being started. Then, set pointer is used to access the density variable in TransAT. Entering a for loop, we loop over the blocks. Within each block, we get the total number of cells, and we set pointers to access the variables: pressure, u, velocity, and each alpha row. Then we enter in a loop over the cells. We set the alpha row variable for each phase by multiplying 0.25, our desired volume fraction, by the density of each phase. We also set u velocity and pressure to 0. Once the loops are finished, we print a final statement showing that the initial conditions are finished. With our initial conditions file, we can then run the initial conditions and ensure that everything compiles and runs all right. With the initial conditions complete, we'll set the number of processors we want to run and run the simulation. With the simulation finished, we'll open up ParaView and load the data for visualization. We'll view the color of density, and we'll skip to the end of the simulation so that we can rescale the data. Now we can go back to the beginning and play the entire animation. Here we can see the stratification of the 4 fluids in the domain.